Here's our lecture for section 3.9 in our calculus book. This focus is going to be on derivatives of a new kind of function, function having to do with exponential and logarithms. We start with the idea that we'd like to find out the derivative of the most general exponential function a to the x. I don't know what a is, some base. Let's assume that it's positive, but let's just say we want to find the derivative. So let's say we apply the definition of derivative to that function. The limit as h approaches 0 of a to the x plus h minus a to the x all over h. There's our definition. Okay. But then we notice that I can factor out an a to the x here. So I get a to the x times a to the h minus 1 over h. Okay. And then there's sort of one more thing going on here. This a to the x doesn't have any h's in it. It's not affected by the limit at all. So that a to the x can go all the way to the outside of this limit, that definition. Now, you say, well, what does that tell us? Well, one, we know that the derivative of a to the x is a to the x times this thing. But that thing, this limit as h approaches 0 of a to the h plus 1 minus 1 over h, it is itself a definition of something. It is the definition of the derivative of that function at x equals 0. So this limit is not an expression. It is a constant, because functions have their tangent lines may vary from location to location, but when we talk about the tangent line slope at a particular location, it is a value, not an expression. So in other words, to summarize all that work, if I want to take the derivative of a to the x, it's going to be some constant times a to the x, where again, this constant is the derivative of a to the x at x equals 0. Okay? So now that we get that idea, is there some value of a that will give us a slope at x equals 0 of exactly 1? Well, we can do a little exploration to see if that is true. Let's go to our calculator. I'm going to open a new document. It's going to have a calculator page, and I'm going to show you some functionality of the calculator that I haven't talked about before, and that is under Menu, under Calculus, under option number 2, derivative of a point, I can say I have some function. Its variable is x. It's the value that I want to find the derivative at is at 0. And I can say, okay, well, great. How about 1 to the power of x? I wonder what that exponential function's derivative is at 0. I hit enter, it's 0. Well, remember, I'm looking for 1, so that's not it. Let's go ahead. Instead of retyping all of that, I'm just going to edit this. How about I change, instead of the number 1, I'm going to change it to the number 2. Natural log of 2. Natural log of 2, not equal to 1. In fact, natural log of 2 is a point, so I'm a little bit short here. Okay, how about, so if that's the case, how about 10? Make it a lot bigger. Oh, that's too big. So if not 10 and not 2, and 2 is too small and 10 is too big, how about I go something in between? How about 5? I'm going to start using natural control times enter, so I get always a decimal version. Nope, that's too big. How about, I don't know, let's go with 3. Control enter, just a little bit too high. All right, well, how about not 3 is too high, 2 is too small. How about we split the difference? How about 2.5? Oh, 0.9, too small. So how about I split the difference between 3 and 2.5? How about 2.75? Just a little bit too big. How about 2.725? Oh, just a little bit too big. How about 2 point, a little too big. How about 2 point, just 7.2? Oh, a little too big, but just a little bit. How about 7.21? And we could play this game a lot. We're just a little bit too low. But maybe you're seeing that the number, the special number, this number that's between 2.72 and 2.71 ends up being the value of the constant E, 2.7128, 828, right? So it ends up being that a special thing is that the derivative of e to the x, e is that special number, is e to the x, and again, times 1, because we found that that constant was 1. But we'll just memorize it as, and I said memorize, so therefore stars, we're going to memorize that derivative of e to the x is e to the x. Okay, now, what if we get something more complicated? What about the derivative if it's e to the x plus x cubed? Well, what's our rule? Our rule is going to be repeat and then multiply it by the derivative of the inside. It is a composite function, the e function being the outside function, the x plus x cubed being the inside function. So how about 1 plus 3x squared? Great. Now, what about this function a to the x though? We had said the derivative of a to the x is some constant times a to the x. Do we now have enough insight to find out what that constant is? Well, let's try this out. Let's say y is equal to a to the x, and we're going to take the derivative of both sides. All right? Well, here's my dy dx, no problem there. But let me think about this a to the x thing. A to the x can be thought of as, sorry, a could be thought of as e to the power of natural log of a. Remember that e to a power and the natural log of a, these are inverse functions that cancel each other out. And then we take this all to the x power. Now, do a little bit more algebraic manipulation. We realize that e to a natural log of a to the power of x, well, what we would normally do is we would just multiply those two exponents. Now this looks a lot like this kind of problem. The derivative of this is x times the natural log of x to the power, sorry, e to the power of x times the natural log of a, multiplied by the derivative of that inside function, which is the natural log of a. And then if I undo all of this, this becomes e to the natural log of a, all to the x power times the natural log of a. We find that that special constant is the natural log of a. That the derivative of a to the x is a to the x times the natural log of a. Oh, and by the way, that means this rule here, that means the derivative with respect to x of e to the x is e to the x times the natural log of e. Oh, wait, the natural log of e is just 1. All right, so put this down, memorize that as well. All right, so can we find a point on the graph for this function? Y is equal to 2 to the t minus 3 has a tangent slope of exactly 21. Well, let's start by taking the derivative of both sides of that equation. And I get y prime. And I get, what's the derivative of 2 to the t? Repeat. And then don't forget to multiply by the natural log of 2. When does the slope possibly equal to 21? I don't know. When does 2t equal to 21 over the natural log of 2? Oh, how do I undo that exponentiation? Well, I know I can take the natural log of both sides of this equation. And I get t times the natural log of 2 equals the natural log of, oh, this is a mess, or t is equal to the natural log, the natural log of 21 over natural log of 2 all over the natural log of 2. What a mess. Okay, but what about the derivative of the natural log? How do we find that out? Well, let's talk about combining some strategies from earlier, and that is, hey, I don't know what the derivative of natural log is, but I can get rid of the natural log by taking both sides of that equation and putting it to the power of e. E to the y is equal to x. Now I can use implicit differentiation to take the derivative of both sides. And I get e to the y times y prime, or e to the y times dy dx is equal to 1. That means dy dx, the derivative of y, the thing I'm looking for, is 1 over e to the y. Oh, that puts me in a tough spot. Or does it? Wait, e to the y right here, we said is equal to x. So this is equal to 1 over x. And there's our rule. And put a couple stars next to it, because that's something that we're going to need to memorize. Okay, what's this next one? Find the slope m that passes through the origin and is tangent to the graph of natural log of x. What is the value for m? Let me see if I can draw this out. I've got this graph. Y is equal to the natural log of x. One of the most famous graphs. I've got a line that's going to come through and have a tangent. It's going to go through the origin and it's tangent to that curve. I'd like to know what that slope is. Well, what do we know? Well, we know that the slope of this curve is 1 over x. That's something we know. Oh, here's another thing that we know, that this line goes to 2 points, the origin and this other point, which is x comma natural log x. The slope between those 2 points is difference in the y values divided by the difference in the x values. And it must be equal to 1 over x. 1 over x. So these two slopes must be equal. Now, if I solve this, natural log of x over x is equal to 1 over x. This becomes the natural log of x is equal to, multiply both sides by x to get x over x. You get the natural log of x is equal to 1. And what is that equal to? We'll take e to the power of both sides. I get x is equal to e. So I now know where this tangent line hits, but I want to know what the slope is. Well, the slope is 1 over x, but x is e. So the slope is 1 over e. Okay, so let's talk about finding the derivative of the general logarithm x. It says the rule here is 1 over x times 1 over the natural log of a. Let's see why that is. So if I took the derivative of the log base a of x, according to this rule, I could rewrite that as the derivative of the natural log of x over the natural log of a. But the natural log of a is a constant, so I can pull it out of the derivative part. And I know that the derivative of natural log of x is 1 over x. So that's a pretty useful rule. I want to take a look at this a second time. The derivative with respect to x of log base a of u, where u is some function of x. In other words, I want to look at this with the idea of a chain rule. I still have a natural log of a, and I still have a 1 over u, and then I'm going to finish this off by multiplying it by the derivative of u with respect to x. There's my chain rule. Let's take a look at this in action. I want to take the derivative with respect to x of log base a of a to the sine of x. Well, this says I have a 1 over natural log of a. And I have a 1 over a to the sine of x. And I need to multiply this by the derivative of a to the sine of x. Okay, a to the sine of x. Its derivative is, first of all, a natural log of a times a to the sine of x. And because this is a composite function, I have to take the derivative of that, and I get cosine of x. Well, look at that. This cancels with this cancels with this, and all I'm left with in the end is cosine of x. Let's take a look at this whole problem in a different way. I want to take the derivative with respect to x of log base a of a to the sine of x. But I know some rules about logarithms, like if I have something to a power, I can bring that power down in front, and now I get log base a of a. Wait, I know something else about logarithms, and that is log base a of a, or log base b of b, or natural log of e. They're all equal to the same thing. It's equal to 1. Oh, so all I end up doing is taking the derivative of sine. I know the derivative of sine, cosine. Now, which one of those ways was easier? Okay, so let's keep in mind that simplifying our logarithmic expressions may help us a great deal into finding the answer most easily. All right, so let's do one more. Here's our function, natural log of x minus 3. Find f prime. So let's take the derivative of both sides. F prime. Okay, what's the rule for natural log? Make it a reciprocal, and then we get a chain rule, and the chain rule here is just 1. Okay, so there's our thing. State the domain of f prime. You might say, well, it's pretty easy. The domain appears to be all values not 3. Why is my eraser not working? Okay, the domain is all the values that are not 3. But if you said that, you'd be wrong. Because while it is true it can't be 3, we got to look all the way back to the original function. The x minus 3 not only can't be 0, it must be positive. The internals, the input to the natural log function must be positive. So our domain ends up being all values of x greater than 3. So be careful. Don't just look at the derivative, look at the original function as well. We have one last thing, and that is this idea called a logarithmic differentiation. The idea is that we don't have a rule for finding the derivative of something in the form of a function of x to the power of a function of x. We've got a power rule, which is when x is in the base. We have the exponential rule, where x is in the exponent, but we don't have a rule for when x's are in both the base and the exponent. Here's the idea, though, what we're going to do. Let's start in this example of saying y is x to the x. And I'm going to take the derivative. Sorry, I'm not going to take the derivative side. I'm going to say, I don't know this derivative, but I do know that if I take the natural log of both sides and get natural log of y is equal to, I can take one of those rules for logarithms, I can bring that x down. And now I can take the derivative of both sides of this equation. And I get 1 over y dy dx for the derivative of the left-hand side. This I'm going to treat like a product rule. First times the derivative of the second plus the second times the derivative of the first. Or in other words, 1 over y dy dx is equal to 1 plus the natural log of x. Or dy dx is equal to y times the quantity, 1 plus the natural log of x. Oh, one last step. This y, I know what that y is equal to. So let's change that y into what y is equal to, x to the x times 1 plus the natural log of x. And that's using logarithmic differentiation. We will do that whenever we have taking the derivative of something in the form of a function of x to the power of a function of x.